Ladies and gentlemen, today I'm going to inform you of our latest research, that is, detecting resource utilization bugs induced by variant lifecycles in Android. I'm Yifei Lu, a PhD student from Nanjing University, and I complete this work with my collaborators, Lier Minxue Pan, Yu Pei, and Xuandong Li. Here is our outline. We'll first illustrate what are variant life cycles in Android, and in these variant life cycles, how resource utilization bugs can be induced. Next, we will introduce our VALA, a static analysis for detecting resource utilization bugs in variant life cycles. After that, we will show our experiment on certified popular Android applications, and the last part is our conclusion. So first, what are Android life cycles? They are the models predefined by the Android framework for components like activities and fragments. These models stipulate how the callback methods are invoked automatically during app executions, and we call them the entry points, like the onCreate, onStart method in the right figure. Developers are required to imply app functionalities inside these entry points. The Android official guidelines introduce how the execution orders of these entry points are like in common cases, and we call them the common life cycles. The right figure here is just one kind of common life cycles. However, under specific circumstances, the execution orders of these entry points may deviate from the common ones, and we call them the variant life cycles. For instance, if the framework method finish is called in entry point on create, all the entry point between onCreate and destroy will be skipped, and we call this kind of variant life cycles skip one. So under these variant life cycles, how bugs can be introduced. Let's imagine a resource here. It is designed to be requested in onCreate and released in onStop. When variant lifecycle skip 1 is triggered, entry point onStop is skipped, so the resource may never be released. Moreover, it is also not recommended to move the releasing operations to onDestroy because onDestroy is not always guaranteed to be called. These variant life cycles have largely been overlooked by developers and existing techniques. For developers, it is difficult for them to avoid these bugs because they must guarantee that the design functionalities should fit in all possible life cycles. Existing analysis techniques cannot help as well for dynamic analysis. As we said, variant life cycles only occur under specific circumstance. It is difficult for dynamic analysis to trigger variant life cycles. For static analysis, they cannot find the bugs because their lifecycle models usually include only the common life cycles. It is also not recommended to naively incorporate variant life cycles into these models because it can significantly increase the analyzing cost and the number of false positives. In this paper, we propose VALA, a static analysis framework that detects resource utilization bugs only induced by variant life cycles. As the workflow shows, it has three parts. First, the variant life cycles. We have already embedded three kinds of variant life cycles in VALA. They were summarized from Android API documents. Next, with given APK files, VALA performs context-sensitive data flow analysis to collect sequences of resource utilization operations. We use IO sequences for short. The key point here is that VALA focuses only on resources referenced by member fields. We find that only resources that are used multiple entry points can lead to bugs in variant life cycles. And at the same time, the member fields are the most frequently used methods for the communication between entry points. This insight ensures the efficiency of our VALA. After that, VALA tries to detect IO sequences that may violate the requirements for correct resource utilizations. And for each violation, VALA generates a bug report. First, we select to log for variant life cycles from the Android API reference as it is well maintained, up to date, and supposed to contain all the necessary information. Eventually, we found three kinds of variant life cycles. We named them as skip 1, skip 2, and swap. The skip 1, we have introduced it in the beginning, and here we just can skip it as the time is limited. And the next kind of variant life cycles is skip 2. It targets fragment. And one main method set retain instance is called. Entry points on this tree and on crate will be skipped. So in skip 2, if a resource here is the listener of a video player, if it is designed to be registered not in entry point on crate, but released in on this tree, the listener will never be released, and it is also a resource leak error. The last kind of variant life cycle is swap. Before and after Android 9, the execution orders of entry points on save instant state and on stop are exchanged. So for the negativity, the data here is a Boolean value stored in the field is unlocked. If it is designed to be stored in unsafe instant state or edited in a stop, there can be a data loss error in swap. All the three cases are from real-world Android applications, and to detect these resource utilization bugs, Vala next conducts a content-sensitive data flow analysis repeatedly on each member field in each entry point to collect all the I/O sequences. As we have mentioned before, it is our insight that only resources accessed across entry points can lead to bugs in variant life cycles, and these resources are typically referenced by member fields. Here, the IOs are basically method invocations on resource intents. And for the two kinds of resource utilization errors, we define four kinds of IOs. They are IQ, IEL, SAV, and ETT operations. We collect these IOs from previous works and frequently used third-party libraries. Come back to the data flow analysis. It has three steps, and we will explain the three steps with examples in skip 1. So the first step is to collect all the execution paths. In the example, for the only member field DB, and then the two entry points on create and on stop, we can obtain three execution passes, two in the entry points on create and one passing on stop. The next step is for each execution pass, we keep trace of the aliasing relationship between the member field and other expressions. Here, we use the concept access path intent analysis to represent all the alias to the target member field. Take the first pass as an example. In the beginning, we have the initial access path that is DB, as DB is our target member field. Next, local variable O is assigned to DB, and then we add O to the access path. Moreover, a backward on-demand alias analysis is applied to look for other possible alias that may point to O. As before L1, we didn't know that O would also point to DB. After returning to L1, the forward propagation continues until the end of the entry point, and the access passes remain the same. The third step is to collect the I/O sequence along the intent propagation. For any resource utilization method invocations on the access passes, we translate them into IOs and add them into the IO sequence. Still take the third pass as an example. In the beginning, the IO sequence is empty. When we return back to L0 in the backward alias analysis, we can find that the initiation method of circle light helper is called, and the value is assigned to O. We translate the invocation as an IQ operation and add it to the IO sequence. Eventually, we can get three possible IO sequences from the three execution passes. And with the summarized IO sequences, Vala detects whether they may violate the correct resource utilizations in the variant life cycles. in skip 1 if a violation exists and lead to a resource leak error. 5 conditions should be satisfied with 2 IO sequences S1 and S2, entry point on create and on stop respectively. Third is the guard condition of the variant lifecycle. It requires the invocation of method finish, that is, the statement L3. So the first IO sequences satisfy the requirement while the second one is excluded. Next, as it is excluded as execution passes does not cover statement L3. Then next, we can easily confirm that the remaining 2 sequences satisfy the other 4 conditions, and it means a resource leak is found. For requirement of the other 2 kinds of variant life cycles, you can refer to our paper for more detailed information. And we evaluate our Vala on 35 popular Android applications from GitHub that may trigger any of the variant life cycles. Here, we list their names, their versions, the numbers of their components, fields, and the components may trigger variant life cycles. We also compare Vala with Radar 2, an off-the-shelf resource leak detector. In 8 out of the 35 apps, Vala detected 8 bugs with no false positives, and 7 of them were reported for the first time, and 5 of them were quickly confirmed or fixed. Radar 2 found none of the 8 bugs, and the Radar 2 found 165 false positives. We obtained 2 interesting findings. The first that is, even remanded, developers may produce incorrect fixes for the bugs. For instance, for the bugs we showed in the skip 1, the developers only moved the releasing operation to on this tree. As we said, this is still incorrect and can lead to resource leaks. And another finding is that half of the 6 resource leaks are related to the same third-party library, and it suggests that utilization resources through third-party libraries poses extra challenges on developers. And Vala stopped the analysis immediately on 23 of the 35 apps, as none of their member fields can lead to resource utilization bugs. For the remaining 12 apps, Vala completed the analysis with around 12 seconds and 500 megabytes on average. Compared with Vala, Radar 2 used 7 times longer time than Vala, and the high efficiency of Vala relies on that Vala analyzed a few components and a few fields that can trigger resource utilization bugs in real life cycles. And at last, we can have our summary. In this paper, we identify a novel and important class of bugs that are resource utilization bugs caused by variant life cycles. And we summarized 3 different kinds of dangerous variant life cycles. Next, we developed a technique called Vala. Vala applies context-sensitive data flow analysis to collect IO sequences in entry points and detect resource utilization bugs based on the gathered sequences and the resource utilization requirements. We evaluate Vala on 35 popular Android applications, and the results suggest that Vala is both effective and efficient in detecting resource utilization bugs induced by variant life cycles. And that's all. Thank you. Any questions?